Hey everyone, let's talk about electric potential and electric potential energy. Imagine we've got a large charge right here. It's positive, and you get two smaller charges. Okay, where do these smaller charges want to go? If you put on your forces glasses and you take a look at this, you'll see electric force. You'll see that this negative charge is attracted, and there's an electric field that's going outward from this positive charge, and this one receives an electric force in the opposite direction of the electric field. And likewise over here, this is a positive charge, it's repelled, the electric field is outward from this big positive, so this little positive charge gets a force outward. But now think of it in terms of energy. So like if you take a baseball and you drop it, why does it fall in terms of energy? It falls because there is potential energy built up in the system, and as it falls, its gravitational potential energy turns into kinetic energy. And that's what's happening here. These things, these smaller charges, have electric potential energy, and it's being converted into kinetic energy as it gives up its potential energy, converting it into kinetic. So here's what we have. I have a negative charge in the center now. This negative charge wants to naturally go away. It will naturally convert electric potential energy into kinetic. It would take work to place it closer. The amount of work it would take to place it closer would be equal to the increase in electric potential energy that it would gain. Same thing with this positive. It would naturally be attracted to this one. It naturally will move this way and give up electric potential energy, and it would turn into kinetic energy. It would take work to take this positive and push it in the opposite direction it doesn't want to go. Work would be equal to the increase in electric potential energy that it would gain as we move it away. Kinetic energy equals how much the potential energy of the system decreases. That's how much the kinetic energy would go up. And if we increase the potential energy of the system, that requires work, and the work will equal how much that goes up. Let's take a look at some equations and see where they come from. Remember that work equals force times the distance it moves times cosine theta, and we're doing the electric force, doing the work. The electric force, of course, for point charges at least, is K Q1 Q2 over R squared. Electric potential energy equals the amount of work it takes to build a charge configuration. Say we have these two positive charges. When they're very far apart, they don't have any influence on each other. It takes effort for me to push them close together. The amount of work it takes for me to push them together equals the amount of electric potential energy the system of these two particles now has. So we can calculate that. Electric potential energy equals the work, and our work is due to me forcing it against the electric force. So I can plug in this equation, and when I do that, I end up with this equation right here. Now I've canceled out the cosine theta, and we'll talk more about that when we get to physics C. All right, the electric potential energy then equals K Q1 Q2 over R squared. Notice that it only takes two charges at a time. So if you have more than two, you're going to have to calculate them in pairs and then add up the whole system. Potential energy, electric potential energy, is just like any other potential energy. It's a scalar. It has units of joules. There are a couple of unique things about it, though. We can have zero electric potential energy, but it's defined for us by the equation whenever we're at a radius of infinity. Whenever the charges are very far apart and the radius is very big, electric potential energy goes to zero. Another odd thing about it is that it can be positive or negative. Please don't let this freak you out. The zero is just when they're very far apart. Negative just means it's below that spot. Positive means it's above that spot. Now, since zero is when they're very far apart, then if they go up in energy when we bring them together, like these two positives would, then it takes work to get them into that position. But if I had a negative charge and a positive charge, they're very far apart, then when I move them together, well, they want to go there anyway. They're going to a lower potential energy because I have a positive and negative charge, and in the equation that ends up being negative potential energy. Now, what that means is that if they go from 0 towards negative, that means they would naturally move that direction anyway. If they go from 0 towards positive, that means it takes effort and outside work to place them in that position. So whenever the potential energy goes up, it takes work to get it there. Whenever the potential energy goes down, it naturally does that by itself. So here's a configuration of 3 charges, all of them positive Q. They're on an equilateral triangle a distance s apart. What's the electric potential energy for this charge configuration? Well, we can only calculate them a pair at a time. So it's K Q Q, or Q squared, over S. And then I have 2 more pairs of the same thing. So I just repeat it twice more. And I add them all up, 3K Q squared over S. So since this is a positive energy configuration, it takes work to build this. How much work did it take to create this configuration? Well, the same as the potential energy that was created. So it's 3K Q squared over S. There are many similarities between gravity and electricity. So here's a couple. The Earth has a gravitational field that's similar to an electric field. So here's the electric field around a positive charge. Here's what the gravitational field looks like around the Earth. Now notice the gravitational field for the Earth always points inward because it pulls all mass towards itself. The electric field can be a little different because we can have both positive and negative charge. So this one's positive, so it points out. But if it was negative, it would look exactly the same as the Earth's gravitational field. The Earth's gravitational field strength is actually G, 9.8 newtons per kilogram. In Physics 1, we called that the acceleration caused by gravity, but technically, it's the Earth's gravitational field strength at the surface of the planet. All right, the Earth has a gravitational potential energy similar to the electric potential energy. So say if I was anywhere this distance from the Earth and I had 10 kilograms of mass, it would have the same gravitational potential energy anywhere along that circle. And if I move outward, farther out, then I have more gravitational potential energy out here, anywhere along that circle. These dashed lines are called isolines of gravitational potential energy. Anywhere on there, we have the same energy. We have the same thing for charges, except these would be isolines of electric potential energy. Gravitational potential is a location where the amount of energy depends on the mass located there. So like, for instance, this spot right here, if I put 10 kilograms of mass there, it'll have a certain amount of energy. If I put 1 kilogram of mass there, it'll have less energy. So it has a certain potential for energy based on that location. Electric potential is the same thing. It's the potential for electric potential energy based on the location and how much charge you place there. We have a name for that. We call that V, or electric potential, which has units of volts. It's the energy divided by the charge right here in this equation. Electric potential, V, is a scalar. It has units of volts. I know that's really confusing, V and V, but one is units, one is the symbol. For a point charge or a spherically concentric charge distribution, electric potential will be KQ over R, but caution please, if we don't have a spherical distribution or a point charge, this equation is no good. We ran into that in class and on the test several times. Electric potential can be positive, negative, or zero at infinity, and the lines of constant electric potential are called isolines or equipotential lines. So these are equipotential or isolines. Now, just like when we talked about electric field, we're actually more interested in electric force because then we can use mechanics. Same thing is true here. Electric potential allows us to calculate things easier, but we're still interested in energy. This is an energy idea. So electric potential times the charge placed there equals the amount of electric potential energy. Keep that in the back of your mind. All right, so here's an example. I have a +2 Coulomb charge and a -3 Coulomb charge placed on the 8V equipotentials. That's this one right here. I have a big positive charge in the center. Now let's take a look at the +2 charge right here. Since it's positive, it naturally wants to move away from this one. That means it's going to be moving towards a lower electric potential. Positives always move towards lower electric potential if they can. Anytime we have a decrease in electric potential energy, we're going to have a gain in kinetic energy. So right here, the amount of potential energy that is lost will equal the amount of kinetic energy that's gained, just like when we drop something, right? The amount of potential energy that was lost as it falls equals the amount of kinetic energy it gained. So don't make it hard, just be careful of your signs. Delta VQ equals the change in electric potential energy. And that's V final minus V initial times the charge. Plug it all in here, and we get 4 joules of lost potential energy, which means gained kinetic energy. Let's take a look at the negative charge. The negative charge here would be attracted, so it will naturally want to move up. So negatives want to move up in potential. If it moves from the 8 to the 12 volt line, its final potential will be 12. Its initial potential would be 8. 12 minus 8, negative, times the negative charge gives me 12 joules of kinetic energy. So this negative charge here will have 12 joules of kinetic energy when it gets to the 12 volt line. Just be careful of your signs. We cannot just neglect the signs like we did in electric force and electric field, because we just reasoned out which direction they were going to be. Pluses and minuses tell us where we are in the potential field, and so we have to keep track of them. All right, it takes work to move a charge in the opposite direction it naturally wants to go. So here we have a +3 Coulomb positive charge located in a potential field right here. So there's my +3 charge. Calculate the work it takes to move it to the -8 volt line. So we're on the -11 line. It naturally wants to move towards lower. It's starting at -11. It's attracted to this negative, wants to go down towards -16 volts, but I'm going to push it up this way to a higher potential. -8 is higher than -11. The work equals the change in potential energy. Again, the math is quite simple, and we get 9 joules of work is required for me to push it upward to a higher potential. Remember, potential energy of the system decreases, kinetic energy will increase. And when the potential energy of the system increases, work was required to make it happen. This turns up on the test on a frequent basis, so let's make sure we get this right. How you define your system will determine how you describe what's going on in the system. So here I have an electron starting from rest, and it's accelerating towards a proton as shown. Where does the kinetic energy come from as it accelerates towards the proton? Using the system that only includes the electrons. So if I just say this is my system, how does it get its kinetic energy? Or, question 2, how does it get its kinetic energy if we include both of these charges in the system? If the charge is alone in our system, then the force on it is external to the system. So this electron would receive its kinetic energy because of the external work done on it by the external electric field. Another way to look at it is, all right, here's a charge system that includes them both. Well, then that force is now an internal force, because remember Newton's third law. There'll be a force inward on the electron and a force outward on the proton. That's an internal force in the system. So in that case, when we include them both in the system, then the kinetic energy of the electron comes from the loss in potential energy of the system. So make sure you understand what we just went through. All right, what if we have multiple point charges? Now, we did this lab in class, and what we did is we produced this topographical map of what the electric potential looks like. This charge distribution right here is the same as this charge distribution. We're looking at the same thing. So if you take this and slice it across horizontally, you'll end up with these circles of equal elevation or equal electric potential. All right, I want you to notice a couple of things. If the two charges are the same sign, they will be enveloped by one ring, or this like 5-volt loop that goes around. If the charges are opposite sign charges, they will not. there will be some separator line in between, and there will be a zero line in between. I don't have the zero line drawn on this one. So that's how one of the ways you can tell if they're the same sign or opposite signs. If I put a positive charge on here, it will want to roll downhill. So if I put a positive charge in here, it'll want to roll or accelerate towards the negative. If I put a negative charge on here, it'll want to accelerate towards the positive. So a negative would want to roll uphill in potential, positives want to roll downhill in potential. So here's what two charges of the same sign and magnitude look like. Here's the electric field drawing, and here's the equipotential drawing. They're complementary. So you can tell on here that they're the same sign because they both have a 10-volt circle around them and they are enveloped by one loop. Over here you can tell they're the same sign because the electric field lines both point away. Here's what opposite sign distributions look like. So here is a plus on the left and a minus on the right. Notice the electric field lines point away from the over here you'll notice that we can tell that they are opposite signs because they're separated by a line of 0 volts. This is positive volts over here and negative volts over here, so we could tell this is the positive and negative locations. There's a huge connection between the electric field and the electric potential. So electric field lines are always perpendicular to the iso lines of constant electric potential. So if you look on here, here are electric field lines drawn. Notice that the electric field everywhere is perpendicular to the iso lines. And the field always points from higher to lower potential. So they're always pointing away from the positive towards the negative, so always from highest to lowest potential. And the electric potential and electric field are connected by this equation. The rate change of the electric potential with distance, so it's like a gradient is what they call this, is equal to the electric field strength. So the faster that these potential lines change, the larger the electric field. So the electric field in this region is stronger than the electric field, say, in this region because the equipotential lines are more farther spaced. Let's look at some charged spherical conductors. Say we have an object, could be like a metal sphere like we had on the Van de Graaff, say, or a solid metal object, it doesn't matter. When we place charge on it, we know all that charge moves to the outside surface, right? And I told you in the last couple videos that the electric field inside is 0, right? So why does it have to be? Well, if there was any electric field still inside here, it's a conductor. And so charges would still be receiving a force and being pushed towards the edges of the conductor. So charge continues to flow until the electric field inside is 0. So on the outside, you get kq over r squared, and it decreases exponentially, not exponentially, 1 over r squared, and it's 0 in the middle. What does that mean for the potential? Well, go back to our equation right here. If the electric field is 0, then there can't be any change in potential. So on the inside surface of this conductor, the potential has to be the same, okay? Now that should make sense because think about it in terms of, let's go back, right here. See how none of this is flat. So if I put a charge on here, it'll want to roll downhill or uphill depending on whether it's positive or negative. As long as this is flat, charges inside won't want to roll one way or the other. So it has to be flat. On the outside, we have K, or 1 over 4 pi epsilon naught, Q over R, an inverse graph, but on the inside, it has to be the same. Okay, now let's look at some non-spherical shapes, in particular a capacitor. You cannot use radial geometry equations for a capacitor because it's not spherical, all right? That's key. So we must use this equation right here. Now, let's remember what a capacitor is from class. So remember a capacitor, a parallel plate capacitor anyway. It has 2 plates that are parallel to each other. They're separated by a distance and an insulator on the inside. And they're used to store charge and energy. So what we'll do is we'll load one plate up with positive charge and the other plate will have an equivalent amount of negative charge on it. All right? The charge is the same magnitude on both plates. The electric potential changes linearly between the plates. So if this plate over here was 20 volts and this plate over here was 0, in the middle it would be 10 volts because it changes from 20 to 0 linearly. The electric field inside is constant, like we talked about in our electric field video. Here we go. Here's what it looks like inside. One plate's positive, one plate's negative. The electric field points from positive to negative. It's uniform except for around the edges. And the equipotential lines will be perpendicular to it, and they'll be uniformly spaced. So in this case, this one has 10 volts over here on the right, negative 10 volts on the left. It has 0 volts right down the middle. All right, so calculate the electric field strength inside this conductor. Inside this capacitor. Well, it's not really very hard at all. The electric field will equal delta V over D in this case, the distance between the plates. So that's 20 volts in between and 0.2 meters separating them. So take those, divide, and I get 100 volts per meter. Now, you remember electric field is in newtons per coulomb. So these turn out to be the exact same units. So volts per meter and newtons per coulomb are the exact same thing. For our capacitor, we can use this equation because it's non-spherical. We have a couple extra equations for the capacitor, which we'll talk in more detail when we get into circuits, but the capacitance of a capacitor equals Q, the charge on one plate, divided by the potential difference between the plates. And the reason why we only use the charge on one plate is because the charge on one plate and the other plate are identical but opposite in sign. So the net charge on a capacitor is always 0. So that won't do us any good. So always just use one plate. So the charge on one plate equals the capacitance times the voltage that you hook it up to. How do we calculate this capacitance? Well, it is kappa epsilon naught A over D. Now remember, kappa is our dielectric constant. It's how strong the insulator is in between here. If there's just an air gap or a vacuum gap in between, kappa is 1, like we see here. If it's something else, they'll have to give you what that is. But like if we put plastic or mylar or something in between, kappa will be larger, and that will increase the capacitance, meaning it'll hold more charge per volt that we hook it up to. Epsilon naught is our constant from earlier. You can look it up on the equation sheet. And A is the area of one plate, again, and D is the distance between the plates. The energy stored on a capacitor is 1/2 QV or 1/2 CV squared. Doesn't matter, either one, they're the same thing. One key thing is that this is the energy stored of all the charges inside, and we can use that to like light up a light bulb or run your house if the electricity goes out, things like that. All right, one last thing. Electrostatic equilibrium, and this is a key idea. When two conductors share charge by conduction or contact, charge will flow until the electric potential is the same everywhere throughout the system. So remember over here that we have 0 potential change inside. It's a plateau. And that has to be true whenever we touch things together. The electric potential everywhere through that system of objects connected has to be the same potential, like 10 volts everywhere. And whenever we get that, then we have electrostatic equilibrium. Charges won't want to move anymore. So whenever this V is a constant, the electric field inside will also be 0, and we're in equilibrium, just like we have on the inside of this conductor here. When objects are not the same size, they'll have a different final charge then. So here we go. So I say I have two objects right here, object A and object B. Object A is charged up negative, object B is neutral. Say I touch them or I connect them with like a wire so that they're in electrostatic contact, then charge will flow from A to B because these electrons don't want to be by each other. But when we think in terms of potential, charge will flow over to B until they have the exact same potential. And for a spherical object, we can calculate that with KQ over R. So KQ over R for object A and B must be the same. The K's cancel. So we're left with the charge on A divided by its radius equals the charge on B divided by its radius. So let's say that A is twice as big as B. If it has twice the radius, it's going to have twice the charge in order to have the same potential. All right? Now, remember one important thing, that we still have to have conservation of charge. So let's say that this one starts with 3 coulombs of negative charge, and I touch these two together. A has to have twice as much as B if it's twice as big, but A and B together still have to equal the original 3 coulombs of charge, or negative coulombs of charge. So that would mean that A would have 2 coulombs of negative charge, and B would have 1 coulomb of negative charge. So A is twice as big charge-wise, but when you add them together, they have the original 3 coulombs of charge that we started with. The smaller object will end up with less net charge. However, because our electric field equation is kq over r squared, the radius makes more difference, that this smaller object near its surface will still have a larger electric field than A will because of the r squared term in the denominator. All right, take a breath. That was a lot of information covered really quickly. Our next video is going to go through some examples, and so make sure that we understand what we're talking about. All right, until then, see you then.